My name is Giridhar and I'm from Azim Premji Foundation. It's a great pleasure to have you all here today for the Azim Premji University's public lecture, which will be delivered by Professor Arthur Eisencraft, a distinguished professor from University of Massachusetts. I can say that this is not Arthur's first visit to India, but that won't be adequate, because then I will have to let you into the secret that he spent a long time as a member of the Peace Corps on the borders of Bihar and Nepal. He can in fact talk to you in Nepali also. Some of you may remember that Arthur gave an absolutely riveting, delightful talk last year. That was at the Terry Auditorium around the same time. And we are very happy that Arthur's made time again this January to come and spend 7 to 10 days with us, in fact 10 days with us. His schedule is packed like it always is, but he's always got a hell of a lot of energy, and jet lag, etc. are all strangers to him. He hit the road running yesterday morning after arriving at 4 a.m. His program includes working very closely with a lot of our faculty at the university on science education. He's also doing a workshop with many of our field institute people who are engaged with capacity building of teachers in government schools across the country on science. They're all looking forward to all that, but for today evening we have Arthur all to ourselves. Arthur's topic, of course, is 4 essential questions, and it's all about how do you make science education much more interesting for students, how do you get them engaged better, and those, I think, are the essence of his 4 questions. All of you received the invite, and you've seen that Arthur has indeed a very, very distinguished career, and the profiles described there. I will not take much of your time to do all that. All I can say is we are one of the world's most distinguished science educators with us today, and we should make every use of it. Arthur, if you will speak for about 50 minutes and then leave some time for questions. I've always had this unenviable task of calling a hard stop to the question and answer session, but if Arthur speaks for say 45 minutes and we do a Q&A for 30 minutes, you'll allow me to do a hard stop after 30 minutes. Over to you, Arthur.
Thank you. It's so wonderful to be in Bangalore again. So I have to tell you that I travel a lot in my work, and I was on a plane just recently, and as I sit down getting ready for the flight, this person sitting next to me turns and says, "Do you want to play a game?" And I said, "No, I don't want to play a game." And he said, "It's a good game." I said, "No, I have work to do and I like to relax. I just want to be left alone on the plane." And he said, "Well, can I explain the rules of the game?" And I said, "Okay, what are the rules of the game?" And he said, "I ask you a question. If you don't know the answer, you give me $10. Then you ask me a question. If I don't know the answer, then I give you $10. And I said, "No, I don't want to play that game." And then the plane takes off, and we're in the air, and I'm doing a little work and relaxing, and maybe 1 hour into the flight, he says, "We'll change the rules of the game." I said, "What does that mean?" And he said, "I ask you a question. If you don't know the answer, I give you $50. If you don't know the answer, you give me $10. Then you ask me a question. If I don't know the answer, I give you $50. I said, "I'll play that game." And he said, "What is the height of the Eiffel Tower?" And I said, "I don't know," and I gave him $10. And then he said, "Now you ask me a question." I said, "What is both a mammal and a virus?" And he said, "Oh." And he thought for a while, and I went back to my work. And a half hour later, he said, "You know, on this plane they have the internet. Do you mind if I use the internet?" I said, "No, you can use the internet." And so he spent another half hour on the internet doing whatever he was doing. And then he finally said, "Okay." And he gave me $50. And then he said, "So?" I said, "So what?" And he said, "What's the answer?" I said, "I don't know," and I gave him $10. I said, "Now it's my turn again?" So here's another story. I was once teaching in the high schools, And in America, we have students, I mean, everywhere in the world we have students who have certain learning issues. They don't read as well, they can't do math as well, they don't write as well, so there are problems with these issues they might have. And so I had a group of these in my class, and when it came time to give them an examination, I gave them the examination. I said, go down to that room, it's called a resource room, go down to that room where somebody can help you with the test. And that means we want to find out their science knowledge, so somebody will read the questions to them and see if they know the science. It's not a test to see if they can write well, it's a test about science. Or they might give the answer and somebody might write the answers for them because they have trouble writing. Whatever it is, I gave the students these papers and they went down, and then at the end of the day, the teachers in the resource room said, what are you doing? I said, I thought I'm supposed to send them down to your room to take the test. I said, but you're supposed to take the test and put it in a sealed envelope. And they bring it down, and then we break the seal, and then we administer the test. And I said, why? And they said, what? There were 5 of them. What if on the way down to the test they should read the questions and talk to one another? I said, if they could learn this material in 5 minutes, I would give them the 5 minutes before the test. What kind of questions do you think I'm asking? What kind of questions do I put on a test that in 5 minutes they can share and learn answers they didn't learn in 2 weeks or 3 weeks of instruction? T.S. Eliot said, where is the knowledge we have lost in information? So I'm saying that there are these 4 essential questions that I want to talk about today, which I think are much better questions than what is the height of the Eiffel Tower, which can help us learn, which can help us raise our own questions, and we'll talk about these. So the first question is, what does it mean? So here I have 6 statements of, we'll call them science facts, that we all learn in school. And the school does a very good job of telling us what does it mean. Newton's second law says anytime you see an acceleration, there must be a force. So if something speeds up or slows down, we have to say that you must look for a force. We say F equals ma, the force is equal to the mass times the acceleration. We say energy is conserved, neither created nor destroyed. The total energy is always the same. We say the earth goes around the sun. We say the atom has a nucleus. Mitochondria are the powerhouse of the cell. And water is a polar molecule. In fact, we tell people that the angle between the hydrogen and the H2O is 105 degrees. Our textbooks and classes are dominated by these questions, and we do a good job of answering them. So in one of the projects which I've worked on, Active Chemistry, we also spend time on these questions. What does it mean is an important question. But we try to relate it in a larger context. So what is chemistry? I have to tell you that I had occasion to ask students not what they learned in chemistry while they were studying chemistry, but 5 years after they took chemistry. I said, what do you remember from chemistry? And they said, nothing. I said, there were 20 students. I said, you all took chemistry? Yes, we took chemistry. So what do you remember? Nothing. I said, you must remember something. This was a year of your life. What do you remember? And they said, no, not. I said, please. And then somebody said, I remember the mole. The mole. And I said, good. What is a mole? Oh, we don't know. The teacher used to make a game and say there's an animal called a mole. It's not the animal, it's something else. If they had said it's like a dozen, I think I would have been ecstatic. But they just said, no, we learned them. I said, well, do you remember anything else? And then I said, do you remember about Avogadro's number, since that's related to the mole? And somebody said, two of the students, wait, I remember Avogadro's number. What do you remember about it? And they said, no, I don't remember anything else, but I remember hearing it. I said, do you remember anything about it? And they said, wait, I do remember one thing. What's that? There's a 6 in it. Now, we learn Avogadro's number, 6.02 times 10 to the 23rd. The 6 is the least important number in that 10 to the 23, but what does it mean? They don't know. This is after 1 year of chemistry. So what we try to do in our chemistry project is at least remind them every 3 days of instruction what chemistry is. What is chemistry? Chemistry is explaining macroscopic phenomena, things that we see happening, and then interpreting and explaining on a molecular level. So we hope, and then how do you do that? You use symbolic structure, use a graph or something like that. So for instance, I want students 5 years after chemistry, I want them to know that if they take an egg and they break the yolk of the egg and they scramble it over the heat and it becomes scrambled eggs, I want them to know that this is chemistry, that when the egg went from this raw egg to this thing, something happened at the molecular level to do that. I don't care if they know it's denaturing protein or not, but something happened at the molecular level to do this. And that's what we try to do. So in Boyle's law, instead of just saying that if you take a balloon and you press it, it gets smaller, the pressure increases, and you can measure the pressure and things like that. So at the macro level, we say, well, when you push on the balloon, what happens to the pressure? You push on, you increase the pressure, what happens? You increase the pressure, the volume gets smaller, the balloon gets smaller. Okay. What's happening at the molecular level? Well, the students can draw up the particles and show me what happens when the pressure increases. Why does the volume get smaller? And at the symbolic level, we have something like this graph, which can explain the volume and pressure, and they can do that. So what does it mean? Can have simple recall questions. What is the chemical symbol for calcium? What is the acceleration due to gravity? Which gas is required for photosynthesis? But these are trivial questions that you can look up on the internet so easily. The better comprehension questions are, what are the products when hydrochloric acid reacts with sodium hydroxide? How far will the ball fall on the earth? Or why is light required for photosynthesis? So even in the what does it mean realm, we can do better questions than some of the questions we hear in school. But it's not enough. Somehow, we're left with these facts of science, which I call the artifacts of science. So I once was with an elementary school principal, and she was telling me that the students in her school have to learn the order of the planets: Mercury, Venus, Earth, Mars. And I said, really? And she said, yes. I said, why? She said, well, it's important to learn. It's important to know Mercury, Venus, Earth, Mars, Jupiter, Saturn. I said, okay, you're the principal, you're the educational leader, but when you teach them the order of the planets, please don't do it during science time. And she said, why not? I said, it has nothing to do with science. She said, it is science. I said, it has nothing whatsoever to do with science. What you told me is what's left over after the science is done. It's after the science is done we know it's Mercury, Venus, Earth, Mars, but that's not the science. And Carl Sagan said, science is a way of thinking much more than a body of knowledge. So the science question, well, there are two. One is, what does it mean to say that Venus is closer to the sun? That's the science question. And it means that we say these planets revolve around the sun, and Mercury, Venus, Earth, Mars, that they all revolve around the sun. But even better, how do we know that Venus is closer to the sun than Earth? How do we know that Venus is closer to the sun than us? I can look it up in a book. No. How do the people who wrote the book know? How do we know? What's the evidence we have for this? Now, that second question speaks to science as a way of thinking. How do we know that Venus is close to the sun? So this is a very educated audience. What is the evidence you have that Venus is closer to the sun? There was some very good evidence 18 months ago.
Transit of...
Yes. 18 months ago, in the middle of the day, Venus went across the sun. The transit of Venus. It was in all the newspapers, and you might have looked at it and seen it yourself. So you saw Venus go in front of the sun. It doesn't happen very often. Once every 100 or 200 years. So if you missed it, too bad. But Venus went in front of the sun. And the only way that's possible is if you have the sun, Venus, and the Earth. If it's the sun, the earth, and Venus, you can't see Venus go between you and the sun. So that's evidence. Now, of course, the transit of Venus happens rarely, but we have other evidence. You know that Venus is the morning star or the evening star. So when the sun is setting, you see Venus over here, because you can have the sun, Venus, and the earth. You can't have Venus over there when the sun is over there, because then we would be between the two. How do we know is the science question, and much more interesting than memorizing that. So I go back to these 6 questions, these 6 statements of fact. What does it mean? And I think everybody knew how do we answer the what does it mean, but I think the number goes way down when I start asking, how do you know any of these things? How do you know energy is conserved? How do you know the earth goes around the sun? How do you know water is made of H2O, or the atom has a nucleus? What is our evidence for these things? So I'd like to tell you that in America, everybody knows the earth goes around the sun. Actually, 80% of adults know the earth goes around the sun. And only 49% know how long it takes. So now in this audience, or in Bangalore, I would say the numbers are probably similar. But if I ask you, what is the evidence you have that the earth goes around the sun? The numbers plummet to 5%, 3%, 7%. But not many people have any evidence whatsoever for the earth goes around the sun. Evidence? How do you know the earth goes around the sun? Yes? Excuse me?
Foucault's pendulum?
Foucault's pendulum, yes, Foucault's pendulum is wonderful evidence that the earth rotates on its axis. So the pendulum goes back and forth, and the earth rotates on its axis. So good evidence for a different question, but I like it. Seasons, okay. Well, you could have the same seasons if the sun went around the earth. It doesn't tell me when happens. It just tells me that there's, rays or indirect rays. The earth could be having the sun go. We knew seasons for thousands and thousands of years because it's so important for our agriculture. It's important to know that, it's getting hot. We should plant the seeds. No, don't do it that way. Do it by a calendar, because the weather can vary, and if you plant the seeds too early, you don't have food that summer. So very early people understood agriculture when they still thought that the sun went around the earth. So we knew the seasons because it was important for our survival. Now, if I ask people, why do you think the earth goes around the sun? Because it is 2015 now, they'll say, I think India sent up a rocket once, or America, or Japan, or everybody's sending up rockets now. And they sent up this rocket above the solar system, and the rocket sat there, and they watched the planets go around the sun. And that would be good evidence, except nobody's ever done that, and nobody will do that. And so what is the evidence we have the earth goes around the sun? Excuse me?
Retrograde motion of the planets.
Retrograde motion of the planets. But couldn't it happen if the planets were just wanderers? That was the old explanation. You see, all of these observational things we have in the, were known for a long time. Ptolemy knew that we had this retrograde motion. In fact, we just had it, or we're having it now, the retrograde motion of Mercury, and people are saying, retrograde motion, people won't be on time for their appointments because of the retrograde motion. But anyway, what happens with the retrograde motion is you can explain that when you say the sun goes around the earth and the earth is at the center of the universe, and Ptolemy did that beautifully with all these circles and things like that. So we need to know. But it's so interesting that none of us question this earth goes around the sun. But when I ask you, why do you believe that? It's like, well, I believe it because my 4th grade teacher told me the earth goes around the sun. When I wrote that on the paper, the earth goes around the sun, they gave me a smiley face and a sticker, and everything was very good. And if I wrote the earth goes around the sun goes around the earth, I had to do it over. And that's where our belief comes from. But it's not where the science comes from. And then we have the other questions as well. So how do we know in science? It's not because it's written in a book. We accept carefully controlled experiments. We accept careful observations. And the unacceptable responses are, it's in the book or the teacher told us. Telling me it's in the book or telling me the teacher told me means I listen to authority, and authority's the answer. And science has shown us that's not the way we do things. The growth in our, since Galileo has been that, no, I can do the science, you can do the science, we can all do the same science and find the results, and we don't have to listen to an authority saying this is the way it will be. So if we have laboratory experiences, we want to know what we can do with those, and these are some of the goals of laboratory experiments. We can have better subject matter understanding, but the one I like is this third one, understanding the complexity and ambiguity of empirical work, experimental work. It's very difficult to do a good experiment. All of what we know in science, most of what we know in science, is dependent on experiments. And we must give school children an opportunity to do experiments so that they see how difficult it is, so that they can value the experiments and how well they're done because they give us knowledge. That brings me to the next question, which is there only one truth? So when you do an experiment and you get a result from the experiment, there can be many interpretations of that result, not just one. And so when you have two competing explanations for an experiment, which of the two do you choose? Why do you choose one over the other? And that brings us to this third essential question. Why do we believe? Now, I need your help with this. If I look up the word believe in the dictionary, I see three meanings. Accept something as true, have trust, or have religious faith. Now, in America, have religious faith has taken over the definition of believe. And I don't mean to talk about religion at all. I want to say believe in terms of accept something as true. I don't know how to use the phrase without saying, why do you believe? So maybe you can tell me how I can say, why do you accept something as true, which captures the meaning and is not interpreted to imply religious faith. Yes?
What is the evidence that convinces you?
What is the evidence that convinces you? That's interesting and gets closer to the how do we know. What is the evidence? I think you'll see, and you'll have to tell me with this question afterwards, that the why do we believe is not about the evidence, it's about something else. So let's take a look at some why do we believe questions. In the school laboratory, we have people do an experiment. We take a cart that can on wheels, and we put a clay figure on the cart. And then we take the cart and we ram the cart into the wall. And when the cart hits the wall, the clay figure keeps going and hits the wall. And we say, oh, this isn't good. If that was a person, this would not be good. So what can you do? And we say, oh, if you put a seat belt on the clay figure, well, if you make the seat belt out of wire, it's not very good because then it just decapitates the clay figure. But if you make the seat belt out of a nice thick piece of cloth, then the car hits the wall and the clay figure stays where it is. And they can do those experiments and understand Newton's first law, an object in motion stays in motion unless a seat belt stops it. And we then ask the students to believe that that will happen with their car. And the students have to be thinking, but I'm not a clay figure. The clay figure is 200 grams, I'm 200 pounds, I'm 100 kilograms. I'm 70 kilograms. And that figure is 200. Why do you think the science will be the same for, and I'm not in a cart. I'm in a car, an automobile. Why do you think the cart and the car are the same? Why do you think the clay figure and me are the same? Why do you believe that? What makes you believe that the physics works the same for both? In chemistry, every day
I take these two liquids, and I pour one clear liquid into another, and a yellow precipitate comes out. It turns yellow. Why do you believe that will happen tomorrow and the next day? Why do you believe that? If I look at the cell structure in San Francisco, if I look at a cell under the microscope in San Francisco or in Bangalore, and then I look at the cell structure in Australia or New Zealand, why do I think the cell structure will be the same in those places? Because in Australia and New Zealand, they're upside down. They're way at the bottom of the earth. Why do I think cell structure will be the same? So here's an example. Why do we believe? We say the sun is made of helium and hydrogen. How do we know that? How do we know it's made of hydrogen and helium? Well, the way we know that is we can take a gas like hydrogen or helium, and we can, on the Earth, and we can take this gas and we can look at the colored light which comes off that gas when you put electricity across it. And the colored light for the hydrogen is 4 colors, very precise colors for the hydrogen, and 4 other colors for helium. And everywhere on Earth, whenever I take hydrogen, I look at the spectra, I see the 4 colors. Whenever I take helium, anywhere on Earth, I see the 4 colors. When I look at the sun and I look at the colors coming off, the 8 colors are there, the exact same colors. And so I say, the sun must be made of helium and hydrogen. But why do I believe that? Just because the lines are the same. Why do I believe that? So the experiment I would like to do is I would like to go up to the sun, take a test tube of the sun, bring it back to Earth, and I can do a whole battery of tests on this and really find out if it's hydrogen and helium. But I can't do that experiment. Do you know why I can't do that experiment? Excuse me? I would, right, yeah, it's too hot, I would vaporize. But what if I went at night? So in active chemistry, what do? We ask the students, we say, why do you believe that this experiment in the school laboratory works in the outside world? Why? Can you provide examples of it using in the world? In industry, in the laboratory, we use 10, 15 milliliters of a chemical. In a chemical plant, they're using hundreds of gallons of chemicals. Why do I think what works with 20 milliliters works with thousands of gallons? We've not tested it. Why do we believe it? So maybe the easier question for us is, why do we not believe? So there's a magazine in America called People magazine. I'm sure you have something like that with Bollywood stars and all these people in it. And if somebody were to come up to me and say, did you see People magazine this week? And I said, no, I didn't see it. Usually you see this if you go to the doctor's office. They have them sitting there. I say, no, I haven't seen People magazine. They say, it's 100 pages long. And I would say, oh, okay, sounds right. I don't know if that's a big issue or a small issue, but 100 pages, it sounds about right. But if somebody came to me and said, have you seen People magazine this week? And I said, no. They said, it's 10,000 pages long. I would say, no, I don't believe you. They say, no, I saw it, it's 10,000 pages. I say, no, I don't believe it. Because something happened to me when I heard that number. I said, 10,000 pages, a book is 500 pages, that's equivalent to 20 books. No, I don't believe that that's how big because the person who delivers the mail no, this is not possible. So there are certain things I know which cause me to not believe what some people tell me. So we have, occasionally students come to me, not occasionally, often they come to me after class and they say, have you read this? I heard that, that this happened, and I say, no, I didn't hear that. That sounds very interesting. Can you tell me the article? Or, I'd like to find out about that. It sounds like a very interesting experiment. But other times they tell me about, I read this in the newspaper, and I say, no, I don't believe you. So when somebody comes to me and says, oh, I just read in the newspaper that a woman gave birth to a porpoise. A woman gave birth to a fish. I was like, no, I don't believe you. They said, no, I read it in the newspaper. I said, no, was this a movie? Was this what? No, I don't believe it. So the biology I know says, no, this is impossible. The logic I know means, no, this cannot. So there's something that I do know that causes me not to believe certain things. So my son called me up last year, and he said, I bought you a present. I said, oh, thank you. What did you buy me? He said, an umbrella. I said, okay. He said, no, it's a special umbrella. And I said, what makes it special? He said, you press a button and it opens up. And I said, oh, I've seen umbrellas like that. He said, no. Then you press the button again and it closes. And I said, no, I don't believe you. And he said, no, it's true. I said, no, I don't believe it. And he said, no, it's true. I said, so I thought for a moment, and I said, oh, does it have a battery? He said, no battery. I said, I don't believe you. So we have this principle called the energy conservation principle, that you can't press a button and have all this energy come out, the umbrella goes, and then press the button again and have all the energy come out again. Then press it again, you get energy, just from pushing it. No, I don't, unless there's a battery. That's why I said I don't believe you. We've constructed filter systems after many years. That's why, that's why I suppose you probably have these Nigerian princes who are telling you that you can have $5 million on the internet. Do you have that in India? Has that reached India? Yes. Yeah. So don't believe that the Nigerian prince wants to give you $5 million. If you'll only give, 10,000 rupees as a good faith jet, no, don't do this. So we have these filter systems. In science, we have these filter systems, and as science educators, scientists and science teachers, we forget to articulate these belief systems to our students, this filter system to our students. And I think the reason why we don't communicate it is because we don't know it. It's what Polanyi calls tacit knowledge. You have the knowledge inside you, but you don't articulate it. So, in active physics, we come to this question of why do we believe, and we've broken it into 3 questions that we ask again after every 3 days of instruction with every topic in physics. We say, does this content fit with other content in science? Does this content fit with the big ideas of science? Does this content meet with the requirements of science? So, by the way, I should, you probably want to see the umbrella. I didn't realize that. You see, you press the button and it opens just like he said. I wasn't surprised by that part. But then he said you press it again and it closes. And it does. But to get it to do again, I have to put the energy back in. So my understanding of the conservation of energy said, no, this isn't possible. But when I saw it, I said, oh, now I understand. So let's take a look at why do we believe through these 3 filter systems that I think most science people go through. The first filter is, does this content fit with other content in science? So each discipline has its own set of topics and questions. So in the top picture, we have somebody fishing. And in this kind of fishing, they take the rod and the string, the line, and they go like this, and the string moves in all these different patterns, and then it lands on the water, and the fish bites the line, and you have fish for dinner. If somebody were to ask me, can you describe how the line moves? And I would say, well, that's a good physics question. I can't explain it, but some people can explain it. There is a physics explanation for how a cord moves. So it is a physics question. It's the kind of question that physics likes to answer. On the other hand, If somebody were to ask me, what was Cézanne's influence on Picasso? I would say, that's a very interesting question. It's not a physics question. You do not answer that question with physics. So right away, my filter system says, the first question, yes, we'll handle that question. The second question, no, go to a different discipline to talk about that question. Not saying it's not a valuable question, it's just not a science question. Then in active physics, we say after that, does it fit with the big ideas of science? We have certain big ideas in science which all science uses. And we subscribe to those. Now, where do we find those? We find these in different documents in the science education literature, the benchmark science education, new framework. And what we know is that we should be reminding students regularly of these big ideas, but we often just forget about them, or we think that they're remembering their big ideas. And we have to find ways to keep bringing it to their attention. So in active physics, we ask them, how does it fit with the big ideas? And then we ask, does the content meet the requirements of science for content? Yes. Here are certain requirements. The first one is similar to what Indira said before. In all science, experimental evidence must be consistent with models and theories. So if you have a model or a theory, the Earth goes around the sun, then the evidence we have, the experiments we see or whatever, must be consistent with that. Water is H2O. Must be. If the models and theories are not, if you can do an experiment which is not consistent with the model, then either the experiment is wrong or the model is wrong. You can't be happy and content in science if this doesn't work. You must have that. You must have these working together. The notion that good, clear explanations should be no more complex than necessary. This is Occam's razor. This goes way back. In science, we look for simplicity. A simple explanation is preferred over a more complex explanation. But that's an aesthetic. Who decides what's simple? Who decides what's complex? This is something, a sense of beauty, a sense of symmetry, a sense of a nice way to look at it. And we expect that good theories will have predictive power. A few simple rules in science should be able to explain a large variety of phenomena. The ad hoc theory, for this time only, is frowned upon. So this is part of the why do we believe. Does the content meet the requirements of science? So let me point out why we get into trouble in explaining science to people. You see, we ask people to believe in fields. There are electric fields and magnetic fields, and they're all through the room. There are these fields. Can I see them? No, you can't see them. We can draw a picture of them as lines that go between every two charges, or lines that go from the magnetic poles of the Earth. There are lines, but the lines aren't real. Then how do we know the fields exist? It's like, oh, we know they exist. But how? If I can't see them, can I weigh them? No, you can't weigh them. They're invisible? Yes, they're invisible. Well, how do you know they exist? Well, we use them to explain a lot of things. Well, but they're not, yes, they're real. But there's a person down the street who says that they will, for only 5,000 rupees, they will massage your aura. They will actually move their hands above your aura and make you feel good. Don't believe them. That's nonsense. We don't have auras. We have fields, but not auras. Or we tell the students, you know, we science people can predict the future. If I take these two clear liquids, tomorrow I'll get a yellow precipitate. Tomorrow? Oh yeah, I can do it now, I can do it tomorrow, I can do it next week, I can predict the future. If I take two cars and I bang them together, I can tell you which one will move after the collision. I can predict the future. But there's somebody down the street who says they can predict the future through their astrology charts. Don't believe them. Only we can do it. And we wonder why people are so enamored by these pseudosciences. It's because they don't understand the distinction between what they're saying and what we're saying. Why should they believe the science and not the pseudoscience? And it's the why do we believe question which can help them answer that. So one of the differences, of course, is falsifiability. In science, we expect that if you can come up with some evidence that's contrary to what we know, then you have to change what we know. In pseudoscience, no, whatever you find out is okay. You don't have to ever change your mind. So when I look at these 6 statements of science, why do we believe Newton's second law? Energy is conserved is a wonderful law. It's probably the most important law in all of science, that energy is neither created nor destroyed, the energy before equals the energy after. But you know, if you do an experiment which involves heat at all, you can never get the conservation of energy. You can never get experimental evidence. There's always a little bit missing. And when there's a little bit missing, you say, so it's there, it's not conserved. No, it's still conserved, but there's a little bit missing. That's a very strange belief to have, that you can, and it's like, well, if I do the experiment more carefully, no matter how careful you do that experiment, it will not turn out to be the energy before equals the energy after. There'll always be a little bit missing. So why do you believe this conservation of energy? We like it a lot. It helps us with so much. So if we take Newton's second law, this F equals ma, and you have a rear-end collision in your car hits you in the back, you ask, does the content fit with other content in science? Oh, yes, it does. Force and motion. We study force and motion in science. Does it fit with big ideas of science? Yes, it fits the idea of systems, that the car is a system and the external force from the other car comes in. Does it meet the requirements? Yes. The use of headrest is also consistent with Newton's first law. It works with Newton's first law and Newton's second law. We can explain this. And that brings us to the last question. Why should I care? Now, as somebody involved in kindergarten through 12th grade education, to me, why should I care means, as a teenage boy or girl, 15 years old in Bangalore, or in a Kutcha village outside of Bangalore, why should I care about any of these things? Why should I care about Newton's second law, or energy conservative, or the earth goes around the sun? Oh, it's on your school exam. No. I don't care about the school exam. I don't care about that. So we know that motivated students have higher achievement. And we know that relevance to their lives now will help motivate them. And so students often ask, why are we learning this? And we have 2 horrible answers. Sometimes we say, oh, this is chapter 14. You need this for chapter 15. And when you tell them that, they usually don't ask again because they know, oh, chapter 17, we need it for chapter 18. So this is not an answer. And occasionally, what you say is, oh, one day this will be useful to you. Well, first of all, one day this will be useful is not about now. And teenagers and children believe in now, not one day this will be useful. So it's not about now and it's not about them. And also, I'd say it's the big lie in American education because it's not even true. That has never been useful to anybody after high school. Now, some of you say, wait, hold on. No, solving the roots for the quadratic equation, that can be important. And I say, no, it isn't. But wait, physics and math people solve quadratic equations. Nobody else does. Out of the population in India, nobody is solving quadratic equations after high school. And yet we all learn this minus b plus or minus squared as this is some kind of mantra. Minus b plus or minus squared, b squared minus 4ac all over 2a. Oh. But so what do I mean it's not useful? If you solve quadratic equations in your work as an adult, then you take out your TI-85 calculator, and you plug in the roots ABC, you plug in the coefficients ABC, and boom, it gives you the two roots. Nobody does this anymore. Nobody who has to do this does this. If you have to solve quadratic equations, just plug them into any kind of mathematical, any kind of program on your computer. Nobody is taking square roots of numbers the long way, by hand, as I remember how to do, as some of you remember how to do. Do you remember how to do square roots by hand? Yeah, there you go. Nobody knows how to do that anymore. John Dewey, the great philosopher of education, said, education is not a preparation for life. Education is life itself. So the Why Should I Care talks about education as life itself, now. So what do we do as teachers? We have to respect our students, respect where they are, their age-appropriate perspective. The idea of childhood, of being 9 years old, is not to be prepared to be 17 years old. It's to enjoy life and learning at 9 years old. And so we try our best as teachers. So when we teach physics, we teach the physics of sport, the physics of cricket, the physics of football. When we talk about chemistry, we say, oh, there's chemistry in the scrambling the eggs and the denaturing the proteins. We talk about earth science, we say, what is this global warming? What does it mean? What is the evidence? We ask in biology, what's the implications of using prescription or non-prescription drugs? So we always try to take this science content and put it in a larger context and have the students do projects or whatever, so that they can care and see where it has meaning. So what do I do with these 4 essential questions? Well, first of all, I post them in front of my room, in the classroom, in the high schools. I put the 4 questions in front of the classroom. What does it mean? How do we know? Why do we believe? Why should I care? And what happened was that I got this unintended consequence. One day, I was teaching, and a student raised his hand, and I said, yes, you have a question? And he said, and he pointed to the sign, and he said, why should I care? And I realized that I had given the student an opportunity to politely tell me that he was not engaged. He did not see the relevance. If I did not have that sign up there, he could not say, why should I care, without it seeming disrespectful to me, which he didn't want to do. But the sign allowed him to say, help me. Help me to be engaged. Can you tell me where this is relevant? Now, it's not an easy question, why should I care? Making things relevant is not always easy, but we have to try. And so, these essential questions, I discuss them in class, I assign them as homework, I give them as test questions. They're for all students, not just an enhancement or for the select few that are going to university. They're for all students. Now, of course, those are my 4 questions. The students have their 4 questions. What did you say? Should we write this down? Do we have to know this? Will this be on the test? Those are the relevant questions to them, and I'm trying to move them from the right side of the screen to the left side of the screen so that they ask better questions. Now, to give a more formal parallel to this, these ideas are not new ideas. So Shavelson and Lee talk about 4 ways of knowing. They talk about declarative knowledge, knowing that. What does it mean? Procedural knowledge, knowing how. How do we know? Schematic knowledge, knowing why. Why do we believe? And strategic knowledge, knowing when and where to apply knowledge, which I call as why should we care? In this document in the United States, which is a document we use to test students all over the in the United States to see their progress, they talk about 4 elements of science: identifying scientific principles, using scientific principles, using scientific inquiry, and using technology, which I think can also map onto these questions. In taking science to school, a report about our elementary students and how they learn science. They talk about knowing, using, and interpreting scientific explanation of the natural world, generating and evaluating scientific evidence, understanding the nature and development of scientific knowledge, or participating productively in scientific practices and discourses. Again, maps on. They're all related. In the framework for K through 12, which just came out in the United States, they talk about procedure, content knowledge. What does it mean? Procedural knowledge, also called concepts of evidence. Epistemic knowledge of the constructs and values that are intrinsic to science. Why do we believe? Why do we like one explanation over another? Why do we not believe? And then they talk about a core idea. Relate to the interests and life experience of students, or can be connected to societal or personal concerns. Why should we care? So all of these documents are pointing toward the same way of looking at education, the same important questions that we should be asking our students and demanding that they answer, because that's what science is about. T.S. Eliot said, "Where is the knowledge we have lost in information?" We can ensure through our teaching that we value knowledge over information. The next line in that poem, though, is perhaps more difficult. Where is the wisdom we have lost in knowledge? That's a different talk. Thank you. So now I sit here.
Thank you very much, Arthur.
I can take questions.
So, if the mic can go around and people...
I think I was very clear, so there should be no questions at all, right? No questions.
Okay, so...
I have two questions. One is, I think it was the fourth last or fifth last slide, where you connected technology to why should I care? I'm not clear how those two connect.
Well, I think one of the reasons why students may care about some of the topics we learn in science is because of the wonderful technologies that they're going to get from these technologies. And they say, oh, you mean if I understand this, I might be able to build a better Nintendo game? Yes. I might be able to build a portable microwave so I can just put it in my pocket and then warm my lunch up when I get to school? Yes. So all of the technology, students are really quite taken with technology, especially the communications technologies, the medical technology. They want to help people, so the medical tech. So if you can relate it to technologies, I think they see a relevance in that for their lives or for things like, to make life more fun or less suffering for them.
Thank you. And the second question was, you didn't tell us what is the convincing evidence that the Earth revolves around the sun?
Oh. So the original evidence was in the why do we believe, it was the aesthetic. It was that Ptolemy had built this beautiful system for astrology because people cared. I mean, you look up at the stars and you see the stars, and you see the sun every day. It goes up and down. The moon goes up and down. This is very interesting, and people were always searching for how does this work. But we also knew that we're sitting here, we're not getting dizzy, so how can we think the Earth is spinning on its axis or traveling? It's like, no, come on. And we get the number, so we felt very content with the Earth is the center of the universe. We're the center of the universe. This makes sense this makes me feel good. I'm the center of the universe. Some people still believe they're the center of the universe. But we were able to use Ptolemy's charts for hundreds, thousands of years. We can still use Ptolemy's charts to predict where the planets will be and where the sun will be and the moon will be every day. They're that good. When the eclipses will happen, they're that good. However, Copernicus said, no, if the Earth goes around the sun, instead of having hundreds and hundreds of epicycles, because the beautiful patterns of Ptolemy are these like spirographs. Everything is moving in circles. Oh, circles because circles are a beautiful shape. They have perfect symmetry. So the aesthetic is, oh, the circles. So Ptolemy has these circles and circles upon circles upon circles, and it explains it just perfectly. But with Copernicus, you cut down the number of circles by 100-fold, and now you only have a few circles. So when the Earth goes around the sun, or Mercury, you have these circles now. The retrograde motion, somebody spoke about, oh, you need a few extra circles, but it's really much easier. And so it was like, oh, that's a nice idea. And then what happens, though, is Kepler looks at this and he says, those circles just aren't good enough. And he puts the Earth, the sun at the center, and he draws a circle. He said, no, oh, wait. If they aren't circles, but they're ellipses, you only need one ellipse for the Earth, one ellipse for Jupiter, one ellipse for Mercury, one ellipse for Mars, and they work perfectly. One ellipse can explain all the motions. How one ellipse for each, not 10, not 100, not 1,000, one. So people say, one is really nice, and it's an ellipse. We like circles. Circles are perfect. Circles are like godlike, ethereal. No. Give up the circles. We don't care about it. They're ellipses. Oh. And then what happens is, Kepler, even when he gets close to the ellipses, there's a guy named Tycho Brahe who's observing the stars. They don't have telescopes yet. They're observing the stars. He has this big, bigger than this stage, protractors that he can measure angles, and he looks at the star and he writes down every night where the stars are. Tycho Brahe likes to party a lot, drinks a lot. Kepler grew up in a monastery. Kepler comes to Tycho Brahe saying, I heard you have some really good data. And Brahe says, yeah, have a drink with me. He said, I don't drink. He said, I'll show you the data. And the two of them don't get along very well at all. 1 minute, like 1/60th of a degree, and he said, no, Tycho Brahe would not have made this big a mistake. And so he goes back, and then he finds the correct ellipse. And he says, oh, look at this. They travel in ellipses. The period squared over the radius cubed is constant for every planet. They sweep out equal areas at equal times. Those are my 3 laws. They work for every astronomical body. People say, wow, that's good. And so now people are beginning to say the Earth goes around the sun for aesthetics. Then Newton comes along and says, you know what? If you think of gravitational bodies as attracting one another, I can explain all of Kepler's 3 laws in one equation. This is the universal law. You'll say, that's really nice. We're going to believe the Earth goes around the sun. And then somebody said, if the Earth goes around the sun, if I look at this star when the Earth is here, and then the Earth goes 6 months later, and I look at the star, the angle would be different to the star. It's the same way that if you hold up your finger and close one eye and look at me, line up one finger with me, like this, and then open up the other eye, you'll see the finger shifts. If you've never done, have you done this? Try this. Hold up a finger with one eye, close one eye, and line it up with me, with one eye. Now don't move it, move the other eye. Do you see how it shifted? And the same law on Earth works in the heavens. That was Galileo's huge contribution. That, no, not everything goes, see, there's religious in here, there's all, so the idea that not everything goes around the sun, see, the idea was everything goes around the Earth. And then Galileo in his telescope saw planets, moons, moving around Jupiter. And he said, not everything goes around the Earth. Those planets go around Jupiter. Those moons go around Jupiter. People said, oh, not everything. And so you have these schisms and ability to change it. So I'm sorry, too long in a little physics lecture. I'm sorry for those. Other questions?
Apparently, Galileo saw the full Venus like a moon, which can only happen if the Venus goes around the sun. Whereas if everything like Ptolemy's thing will not show a full Venus, it will be always crescent kind of Venus. I read somewhere that this was a positive proof that things went around the sun rather than things going around there.
yes, the phases of Venus was other evidence of that things are, the position of them and things going around the sun. So there's a host of other evidence like that. And then, of course, as you know, Newton's law could not explain some of the motion of Mercury. And so, as good as Newton's law was, it took Einstein to say, oops, I think there was a mistake there, to explain the experimental anomaly of Mercury's path. This is just history of science. It's just wonderful. Anything in astrology that is science? Well, I think that recording the data and the position of all the planets was certainly an enormous feat of observation. About the forces, the difference in the forces on me, whether Jupiter is in one place or another, is similar to whether I'm standing on the stage or sitting in the audience, and standing on doesn't affect our lives in that way. So I would say, no, there's no evidence, but it's fun to do. But I wouldn't stake anything of value on it. It's fun to do. So, and I want to certainly respect that. If you look at your astrology signs and it says, oh, I'm going to meet somebody important. Oh, this is exciting. That's okay. You can get excited. If you see in the astrology chart, oh, today will bring you good luck, or today, that's fine. Be happy about this. But if it says, don't meet with someone important, and you have a job interview for that day, no, this is not going to help you. It's fun. It's just another, everybody loves people, hearing about what their future might be like. But we're in control of our future, not the stars or the planets. Oh, he's in charge of calling up people. Yes.
Yeah, since this talk is about education, so I have this question, the example which you gave about the quadratic equation, which nobody cares, and even I don't care now that I've grown up now, and I always struggle with that equation. Why countries like US, or say even matter India, they sometimes get obsessed about this students getting low math scores, which is exactly, for example, for the many students, it's not relevant. And why do they care? Why they are obsessed about these scores? Or where I occasionally come across articles where stating US students are performing in maths at very low whatever grade compared to the Indian counterparts. Why is that comparison? Why it is valid? But given that the learning is important, and
Well, first of all, I wouldn't say knowing the quadratic equation is of no value, because when you have a child in high school, you can help the child if you remember how to do this. So in that way, it's still of some value. But the question is, why do we still teach this? Why do we still test it? Was one part of the question. Then what is the obsession with the math tests? So it is very interesting, and this is a puzzle which I'm working on. I don't know if in India, we have two kinds of exams we give in America. One is called a closed book exam, like a state exam is closed book, that you have no books to help you, you have to take the test. And the other is called an open book exam. You can use your notebook, you can use your textbook, and we'll ask you questions. And of course, when you can use the book and your notes, you ask different questions than when you can't. Well, most people now, and if not now, in 10 years, everybody's going to have the internet 24/7. I have the internet wherever I go. I'm in Bangalore, I have the internet. So the question is, what should our tests be like if we make them open internet tests? Why do we deny students this tool which is a part of their lives? If we have open internet tests, what questions will we ask on our examinations? And I suspect these questions are much more of those that we'll ask. The obsession about tests are, certainly we live in a worldwide community, and we're very competitive. America, the United States, has had a great deal of economic success, and it's come about because of our educational system and our innovation and things like that. We need an educated citizenry. We have this from the beginning of our country, is we want an educated citizenry to vote, to make good decisions. We worry that if we don't have students who know math, that we won't have that next generation of people to help us continue our economic productivity. At one point, some years ago, we could take people who had very good educations from other countries. We do it with India. People who get incredibly wonderful educations in India, the very best students, and we say, come to America and we'll teach you some things, and you'll get a PhD in America. And then we say, oh, why don't you stay in America? And there was a time when everybody said, yes, I'll stay in America. And so we could import the people who had these great educations. We could import them from India, from China, from Germany, from England. We could do that. Now the world has changed, and a lot of people who get the PhDs who come from India say, no, I want to go back to India. And so we start saying, well, where are we going to get the people to help us if they don't want to stay here anymore, because there are reasons to stay in their home countries, of course. So we worry about these things, and we want to improve the education. Now, when we find out that we're not doing as well as other countries, we get nervous. And we think that that will, provide the politicians with the impetus to give us more support for education to change it. Of course, when you look at the exams and say people aren't doing well on the exams, you a priori are assuming the exams are good exams, that they're testing the right things, that they're testing what really is mathematics, and not testing something else. So there are politics, there's economics, but we know that science drives the economic engine of our world, and certainly of our countries. And so we want more people to have an understanding of science, not just to do science, but to help make decisions about science that will benefit all of us.
Keep your hands raised so that I can just catch them. 1 there, 2 there, 3 there, and 4. Can I do these 4 here, please? Okay. 1, Firdaus, wahan pe. No, I want to finish that side, sorry, and then come back to you, sir.
I have 2 questions. So my first question is, you speak about aesthetics of science.
I'm sorry.
You speak about the aesthetics within science when you spoke of that. But at the same time, when you spoke about the influence of Cézanne on Picasso, you said that's in a different department. So is there still such a big divide between art and science? That's one question. And the second question is, what does physics think about meditation? Because, meditators often speak of achieving a stillness from a vibration.
I'm
So
sorry. Oh,
what-
meditation.
Yeah,
I thought you
yeah.
said medication, like pills.
No, meditation.
Thank you.
Yeah.
So the first question is more of a philosophy of art question. What is beauty? And how do we define what beauty is? So, of course, some people love Cézanne, some people love Picasso, some people love a black square on a gray background and say, no, that's beautiful art. So that's one kind of beauty. There's music, and some music is beautiful, and other music I don't think is beautiful. Some of you don't think some music is beautiful. So there's very much a personal understanding and resonance with these fields. There's also a beauty in mathematics. There's a beauty, it's a different kind of, music is not the same as art is not the same as mathematics or science. They're different, and we have different aesthetics for them in defining the aesthetics. I wish sometimes I wish I could show the students a theory in science and have them just sit for 15 minutes as they would listening to some music, to sit for 15 minutes and to try to just meditate on the theory and enjoy it. But we don't have time for that in school, and nobody has the patience to sit for 15 minutes. But this idea of the Pythagorean theorem for 2,000 years, that any triangle you draw, there's a relationship between the three sides. Any triangle you draw, it's like, and it doesn't, it holds sway. It just is this wonderful thing. There are ways of looking at the world that are just extraordinarily beautiful if you prepare yourself to understand the math, to understand this. So that's what I mean by an aesthetic. I mean, there's no question that when you show people, when a new theory comes, that people say, that's so beautiful. In fact, Poincaré, the mathematician, said, in my work, I have tried to unite the true with the beautiful. But when I had to choose one or the other, I chose the beautiful, not the true. Now, Poincaré and the other great physicists, mathematicians, have such an intuitive sense of beauty in the world that what they choose as beauty turns out to be truth later on. So when Poincaré says, I chose the beauty over the truth, that was only the temporary truth. It turns out the real truth was more aligned with his beauty. And Einstein had that sense of the way the world could be in physics. And, and so that aesthetic drives them. Dirac, the great British physicist, he said, if the mathematics is not beautiful, it's wrong. Your theory is wrong if the mathematics isn't beautiful enough. I mean, that's how driven they were by this sense of beauty. Meditation, I think there are too many things we don't know. There are a lot of things we do know, and there are too many things we don't know, which makes the world a fun place to be. So I certainly have no idea of what would be going on in meditation, except and I don't know, if you're saying meditation will allow you to levitate off the floor, I'm going to say no. If you're going to say meditation will allow you to have different kinds of thoughts or I think there are many ways to think, and meditation is one, and we certainly don't understand how we think, how our memories work, how that. So I'm certainly not an expert, and I should be meditating more, and whatever.
We have just
Question is more in terms of the science and belief systems. So I agree with the fact that we need to have a scientific temper and there should be some basis of believing in something. There is a lot of evidence that is coming up saying that obviously there are a lot of claims recently by political leaders saying that the elephant god is because of plastic surgery and so on, and somebody says that the mythology was the origin of some test tube. All these are irrational and there is no scientific basis for that. But there's increasingly a lot of evidence saying that if you believe in certain religious beliefs, there are linkages to the better mental health, well-being, that could strengthen the institutions of something like marriage and so on. People are using these belief systems to cure depression or for mental health being. Does that validate that belief? I mean, so is that science, is my question. Because people are saying that you can extend these notions of these connections between belief and medicine. Somebody can use it to validate saying that this is science for you.
That was a very long question.
Well, yeah. So the question about religion, faith, and science, I don't think it has to be a debate where people are forced to make one decision or another about what they believe. Certainly, people have struggled with understanding the world for thousands of years. So we have the mythology of Ganesh, we have Hanuman and Sita and Ram in the Ramayana, we have these stories, we have the Bible, we have stories of trying to explain how we came to be in our lives. I think that religion has a very important part in some people's lives, and it brings them a great deal of comfort, and I wouldn't deny them that comfort. I think that we go through certain difficult times in all of our lives where a loved one dies, and religion tells us what to do, and that's very comforting for people. And I would never say don't do that, because people have been suffering for thousands of years, and the religions came about to help you deal with those sufferings. So I think that that's fine. I think that it's not a science in that it can't be falsified, as I said before. So if you say, what bothers me is that people point to evidence and say, oh, so now we know, this is evidence that God exists. And it's like, well, why do you need evidence? Because there's no evidence anybody can come up with where somebody says, oh, you've proven God doesn't exist. That's impossible, because whatever it is, God made it that way, so God exists. To seek scientific evidence of the existence of God or the non-existence of God, I just don't think it's possible. It's not a science because you can't falsify it. But I agree, it brings great comfort to a great many people. It has its place, and science has its place.
Hence my questions and comments. It's very pertinent to note that your terms of reference are all Western, and naturally so. In the Indian tradition, the earth was never the center of the universe for many, many thousands of years. And there was no doubt about this. Secondly, while you're talking on this, I just want to condense my questions. Now, the teaching pedagogy is on the academic bent. Wouldn't it be better to start off with the practitioner's bent and do the reverse? Say, you want a particular thing done, how does it work? Go back to academics. Now it's the other way around. At least in India, you go through books and books on academics, and finally you might just about land up with a little bit of that practitioner's part of it. Thirdly, the other day there was a news item that MIT scientists had found out that the planetary positions at the time of your birth have a certain correlation with your life. And fourthly, this is MIT's, you can check it up in the news. This is about 1 month back. And fourthly, you're talking about the exam system. Is scholastic ability any gauge of your mental acumen? 1. 2, is formal academic achievement any barometer of your faculties of mind?
So that's a lot of questions, and certainly I appreciate your, I admit that, of course, I have a very Western view of science, and in fact, the language I speak has a Western influence on my thoughts as well. So Asian, I recognize that when I think about these things. I can't apologize for it. It's what I do, what I am, my life. As far as the, no, I'm very, we have to make a distinction. The larger question, I think the important question for all of us is that there are two ways of looking at your mindset. One is the fixed mindset, that your genes tell you how smart you are. Oh, this person is good at math, or this person is good, and it stays fixed, and we can measure it, and that measurement is a good measurement, and that's how smart you are, and that will define what you do for your whole life. A fixed mindset. Then there's another philosophy, which is a growth mindset, which speaks to the mind as being a muscle which just has to be exercised. And everybody can learn math if you try. And everybody can do this if you try. And everybody can do that if you try. And the growth mindset turns out to yield much greater benefits if you adopt that. that, oh no, if you have the fixed mindset, you're afraid to take on extra challenges because it might prove that you're fixed mind, that you're not smart enough to do this. Well, if you have a growth mindset, you take on challenges because they're interesting and you grow. So I would never say because of some paper and pencil test, we can look into the inner soul of people and see their value and worth. And it bothers me that we have a society where too often students get discouraged, very good students, because a university looks at a few numbers and says, oh no, you're not worthy to be at our university. And I think, oh, they know that they really know me. When in fact everybody else who knows them think they're wonderful people. So we have to be very careful how we use these numbers. But the growth mindset is a philosophy where, no, we can all do this and all our children can learn all these things if we encourage them to, because it's not a matter of genetics or it's a matter of wanting to work to learn them.
Any other last question?
I think you had this gentleman here.
Isn't the entire science involuted into plants and animals? And it is only a question of evolution that is happening. Because without Newton and other things, monkeys hop from tree to tree. A simple homemaker gives birth to many children, and not all the Nobel laureates put together can do that today. Involution and evolution, that is the basic question.
I'm not sure.
Perhaps he can answer the question also. Would you like to spend a couple of minutes on it? You must obviously have thought of it. So please speak for a couple of minutes on this.
A lot of egotism that, it is doing something wonderful, whereas it is already involuted. Science is already involuted in plants and animals and living creatures. The only thing is we are rediscovering it. So that's it. It is involuted in us already.
So certainly a wonder and a beauty you find in the world. And yes, although we understand much more about birth, and we understand much more about the process of an egg and a sperm meeting and producing a human being, when you see that child for the first time and you see the 10 fingers and the little nails, and you have to have some part of you, no matter how scientific you are, to say, this is a miracle. So I think we all agree with that.
So just a few very small phrase. Thank you very much, Arthur, for today. Thank you, everybody, for being such a wonderful audience.